What's good, YouTube? It's True again with another Cafe Yocto episode featuring the Fi-Core AM62X system on module and development kit. Today's video, we're going to be walking through a number of these cherry-picked peripheral guides out of the Fi-Core AM62X developer wiki. Specifically, I'm going to look at GPIO, the display peripheral guide, and the Wi-Fi guide. So check out these specific guides for more information on what I'm going to talk about in the video today, and let's get into it. Alright, I got my Fi-Core AM62X development kit booted into Linux. I want to control some GPIOs. What's a good place to start? Well, I recommend taking a look at what the Linux kernel has enumerated for you. What GPIOs does it know about? And the way we can check that is we can just output this file here in /sys. This is also known as sysfs in Linux. And then in sys kernel, going off memory, and then debug GPIO. So this is the file that aggregates all the GPIO information the kernel has. Cat that file, and we can see here some output. Let's walk through it. So the GPIO chips 0, 1, 2. These are actual subsystems here. This is the physical address in memory. These are GPIO subsystems in the AM625 processor. GPIO chip 3 is a little different. It's an I2C based GPIO expander. We can see it's on bus 2. This is the I2C address. This is the actual driver or chip name. I think they're the same name. And this particular I2C expander is giving us 8 GPIOs. These are the specific GPIO instances. And in this case, this expander gives us the ability to name them too in the device tree, the Linux kernel device tree. But these are the actual device nodes that these GPIOs are associated with. So these I2C-based GPIOs, this particular one is being used as a reset signal for HDMI. This one here is user LED 1, user LED 0. The actual GPIO subsystem in this AM625 silicon, we have this guy coming out of this module, home. What the heck is home? Well, home is actually going to correspond to this S1 user button here at the tip of my finger. One nice thing about this debug GPIO output here, we can actually see that home is configured as an input, and we can even see the state on that pin. So if I actually hold home, S1, and then I run this command again, I can actually see that the input state of home changed. It goes high when you hold the button. And again, it goes low. Now I've ran that command without holding the button down. I can see that went low again. So here we could actually use this debug output directly if you wanted to. You could parse this output and you could get the input and output states of these GPIOs. These GPIO inputs, I believe they're exposed by the GPIO keys driver. There's some other ways that you can like generate the actual type of button press. There's more information about that in the GPIO peripheral guide. Let's move on to outputs. How might I utilize one of these pre-made user LED outputs for myself here? Well, the user LEDs are actually set up with the GPIO LEDs driver, and the sysfs interface for controlling those can be found in sys class LEDs, and then in here you would have a directory for each device. So we got user LED 0 that we want to target. What files do we have available in that device directory? Well, we have these files they literally are exposed by the kernel for us to control the device. So we can write values, we can read things from the files in here. Well, for the LED driver, you wouldn't read anything. Pretty much, we would just write to the brightness or maybe the trigger file and essentially control the device. We can turn that LED off. I should also point out, user LED 0 is the red LED here at the tip of my finger. There's 2 LEDs. Sorry about the video quality. More people watch me, I get more funding. But we could turn off the red LED like so. Here, sys class LEDs, user LED, and then to that brightness file, we should see the red LED turn off. And we could turn it back on with by writing a 1 in the same way to the same file. Boom. User LEDs, user input. Let's talk about displays. The AM625 processor from Texas Instruments is pretty rich in multimedia capabilities. It's got a graphics processor. It's got 2 LVDS display interfaces, as well as 1 parallel display interface. And here on the Phytech Development Kit reference design, we've taken that parallel display interface, enabled it by default, and we bring it out to this parallel to HDMI converter, thus facilitating this HDMI connector. And that's enabled by default. So if you boot up with an HDMI monitor connected here, you'll get display output by default out of the box with the pre-built software here with Alpha 1 DSP. That's not so exciting. That's pretty easy. Everyone's pretty familiar with HDMI. Let's do a little something more custom and showcase graphical user interface capabilities. And to do that, we're going to utilize this X55 connector here in the bottom, this LVDS 0 interface. As a 40-pin connector. Now, before we can really connect anything here, or connecting anything in general when it comes to external hardware, let's first power off the kit. And we can do that together here. The reason for that is, let's say our display connector goes at an angle, you misalign and the wrong pins touch each other, you run the risk of frying something, either whether it be the SOM or the display we're going to look at here in a bit. And we want to avoid that altogether. So power off the kit, remove power completely. This is something you want to do. This is best practice. So with that completely powered up, now we're free to connect things here. Today we're going to be connecting up the LCD 185 LCD display. This is a capacitive touch display, 10-incher, from Lincoln Tech Solutions. These guys are great. They manufacture LCDs, and they worked with us to create this adapter here that allows this LCD to connect directly to our development kit. Pin 1 actually goes to pin 40. You can confirm that in the schematics. And thus there is a flip in the cable required. The way we connect that up here, with this orientation of the development kit upside down, you'd want these contacts on the ribbon cable face down. This will slide into the connector like that, and you'll know it went in because it'll actually slide into the connector. If you're at an angle, if you're shifted over a little too much, it'll kind of not really slide in. It'll be obvious once you get it right. Slides in, and then the next thing to check is that white to blue transition here. You want that parallel with the PCB. And then you know everything is in and straight. So with that parallel, latch it. That little black latch goes up and down. Push that down to lock it in. And now we're all connected up. I'm going to flip this back over and let's take a look at what happens when we boot it up. I'm going to get this all in frame best I can. And I'm going to prop it up with some blocks. There we go. So now with the cable connected, let's connect everything else back up that provides power. This guy, the USB serial debug cable, right? Well, I even supply 5 volts, so that's why I disconnect that too. I disconnect anything initially here that supplies any kind of power. I'm going to power the LCD first. There on the bottom, and now let's boot up the development kit. Now, in order to enable that LVDS display interface, like I said, it's not enabled by default. We're going to have to interrupt this auto boot process here during the countdown. You just hit any key in the terminal. And from here, let's take a quick tour of the default bootloader environment. So when auto boot occurs, or if I manually specify boot like so, what's going to happen is the boot command is actually the first thing that runs. And as a part of the basic boot command, there is a provision here for running this get overlay boot variable. This actually resolves to whatever you're booting from, so boot MMC, right? So get overlay MMC is defined down here. Let's see, here it is. And there's a lot going on here. Really the juicy bit I'd like to just kind of focus on is this for overlay and overlays. Essentially, the default boot environment is going to load every overlay specified in this overlays variable. What the heck is an overlay? Well, the Linux kernel for ARM architecture is going to ship in 2 binaries. One's the kernel, one's the device tree. And the device tree is a definition, essentially, of the hardware that the kernel's booting on. And that way the kernel knows the hardware and what's connected and what have you. So we can, at runtime, modify the device tree by loading these overlays that kind of tweak or tune the device tree so that you can enable add-on hardware that's been supported in the kernel by default for you. So Phytech has done that. We can enable this LCD display just by enabling one of the overlays we've included in the SD card for you. We can do that like this. So we're essentially setting that overlays and environment variable, and we're setting it equal to this file name. This file could be found in the boot directory of the rootfs partition, along with other kernel binaries. Once we set that, let's save the environment variable. I misspelled that. Save that to non-volatile memory, and then we can go ahead and boot. Now we should see that display come up, and watch the display here in the video feed. There we go, Tux the Penguins, a little Texas Instruments loading bar. And sorry it's poor resolution. It's really just because I'm, recording this with the poor webcam here, the poor little guy. And okay, so now we're up. We have a frame buffer, and this is actually a virtual terminal, essentially. It's very much similar to what I have here. You have a login prompt, it even says Arago project. This is kind of hard to see, but you could connect a USB keyboard to your development kit and type and navigate Linux user space directly using the LCD here. Now, that's not so interesting, right? We're already kind of doing that over here in a serial terminal. Let's go ahead and stop that service, and the way we can do that is with this command. This getty at TTY1. This is the virtual serial interface, and I know that that's the one being used because it actually says it here on the display. Hard to make it out again, sorry. But we can stop that service. That login prompt goes away. And now let's start our graphics framework. So we can this Weston framework is shipping by default in our Alpha 1 BSP, and it's going to facilitate us to pipe camera feeds or images to our display, or launch other types of applications. An example we have here in the development kit is this Matrix GUI. This Matrix GUI actually comes from Texas Instruments. It's a application launcher for launching like various Qt applications and others. We can start it just like this. And there on the display, we'll get this GUI up. And it looks very much like, maybe kind of like an iPad, or maybe other tablets in general. Let's walk through an example. And Chameleon I like. Just to kind of showcase the graphics capabilities. Now this guy, the model of this dude, the animation is kind of strange, but it's pretty impressive how smooth everything runs. Hopefully it's coming through. It's a little choppy maybe, but it's very smooth to the human eye. Maybe not so much in the camera feed that you will see at home, but take my word for it. Buy a kit and you can evaluate it yourself. With that done, we can stop the Matrix GUI like so. And one more thing I'd like to showcase is we can just output images to that display here. I got this PNG actually downloaded from the developer wiki for this product. And we can display that to the frame buffer, or not the Weston framework, utilizing GStreamer pipelines, like so. And so essentially we're using a file source, that's the file, and then we are doing some kind of massaging of this data to output it to a video sync, and this one will automatically resolve to our display here. So if I hit that, boom, there you go. And I got the development kit up on the display connected to the development kit. Inception. All right, that's displays. Now let's talk a little bit about Wi-Fi now. So Wi-Fi is not populated on the Ficore AM62X development kit by default on the development kit, but it is supported via the M.2 connector here on the bottom. And we have a number of M.2 Wi-Fi modules supported, and so you could get one of these through us here at Phytech to get this connected to the internet via Wi-Fi. So the way you connect this up, again, we want to make sure that the development kit is unpowered before connecting external modules. This M.2 connector here is going to go in an angle. You kind of see how that goes. And then once it's in, you can press it down. Is that clear? Yeah, it's clear in the video. And it's also a good idea to secure this guy with a little hardware. So I got this little standoff to go underneath. And I believe this is M3. This is an M3 bolt. And we can connect this up very simply, like so. It actually fits perfectly in the mounting hole underneath this M.2. Let's see if I can get it. There we go. Screws in. Doesn't have to be crazy tight, just to secure it down and make sure that those pins are all nicely contacted. Let's flip that over. Oh, one more thing, actually. So if you use the M.2 Wi-Fi modules such as this here, unless there's an antenna integrated on the board, using it like this, you're going to have a terrible time connecting to Wi-Fi, and it's going to be very spotty in terms of connectivity. It'll try to connect, it'll authenticate, it'll de-authenticate, drop itself, continue trying to negotiate, and it's really due to the poor signal quality of this module by default, and modules like this in general. So it's really advantageous to utilize a external antenna. And so here's a very simple one, an example here with this micro FL connector. And this guy can fit onto X2 here, which is like antenna 1 connection. The numbering is kind of interesting there. That just pops on. And now we have an antenna connected to our development kit. I'm just going to let this dangle off the edge of my desk here. And now we can boot up the development kit. Let's do that. Now, on boot up, we're going to have to enable that Wi-Fi. And the way we do that is utilizing a device tree overlay again. Before I do anything, let's set everything back to its default state. We can do that with that command. Let's take a look here. And in the display walkthrough, I've talked about the overlays variable. We're essentially going to have to set that again. However, we're going to just utilize a different overlay that's included in the device, in the BSP, the SD card image by default. And we can grab that here, this file. So essentially, this is going to enable Wi-Fi on the M.2 connector and the signals that are connected to that. Save that environment, and then let's boot up. So on boot for this guy, we can double check that it was detected properly by the kernel with a quick command here. We can essentially parse the boot log. It was up there in this boot log already. It's just too fast for the human eye to catch unless you want to scroll back and find it. So the nice way to reprint out the boot log is this dmessage command, and we just grep for WL, and I'll show you why. So we can see here WL. This is essentially the prefix to the driver for Wi-Fi stuff, and there's a number of them. So this one, WL core, we can see that it kind of fails to load firmware initially. I'm not sure what's going on with that. Again, this is alpha hardware. Hopefully figure those kind of issues out. But it looks like the firmware does eventually get loaded and booted properly on that device. So these Wi-Fi modules often require closed source firmware from whoever manufactured the module, the Wi-Fi module. And so that's why we're injecting firmware into it and booting it. These devices are essentially controllers themselves that facilitate the Wi-Fi connectivity. Now, with WL core properly initialized via this example output, now we can scan for available networks. And we can do that with this scan command here. And I'm just going to grep for the SSID. This is essentially your Wi-Fi network names, the name of the signal. So grep for that. Let's see what we got available here in my office. I got a couple stuff here, a bunch of Phytech networks. This is the one I personally set up, so this is my name. I host this with a hotspot on my workstation laptop, and I configure that to 2.4 gigahertz usually. Depending on the Wi-Fi module, you can support 5 or 4. So you see, like, my Phytech signal has a 5G and then the 2.4. But this one I have specifically configured for 2.4 right now, and we can connect to that by modifying our WPA supplicant configuration here at etc.wpasupplicant.com. We essentially add our network credentials here. So here's the SSID that I want to target, and then here's my password for that network. With that set, make sure you write and quit the file. You gotta save the file. With the credentials provision in that file, we can initialize our connection with this command. And very quickly, we should see authentication happen automatically. Some stuff will get spit out, association completed. Now, I can check my network interfaces, and I should see, an IP address associated with WLAN 0. So now I can go ahead and ping Google and do other things. Yeah, very simple. Let's see. That's about it.
That concludes episode 3 of our AM62X series, but we still have 7 more coming for you. So don't forget to subscribe, and also look at our LinkedIn to stay up to date on when these go live. See you next time.